What's up, everybody? Welcome to another mini lesson on simple machines. Today we are going to cover the screw. This is considered a simple machine, but it is probably one of the more complex ones because instead of a simple inclined plane, for example, like we have before, this is the worst inclined plane ever, but you know what I'm talking about. Instead of an inclined plane, simply doing that, and let me go back to this and erase this guy. Instead of a simple inclined plane, go like that, we have an inclined plane that is wrapped around a cylinder. So the definition of a screw is an inclined plane wrapped around a cylinder. So if you're taking notes, that should be the definition that you need to remember. Like that. An inclined plane wrapped around a cylinder. It is really powerful. There's some things that we have to know about screws, some of the terminology. The first one is going to be this guy here, and that's called pitch. So pitch, and we're going to simply call it P in many instances, is the distance between threads. And that's pretty straightforward. You measure this in here. It could be measured in inches, it could be measured in millimeters, and unfortunately, the United States has two different ways that we measure things. Of course, we use metric and we also use imperial. So we might be switching back and forth depending on what kind of screw it is. So anyway, so pitch is going to be the distance between threads. And that is another one you are going to have to remember. All right, the other one is going to be TPI. TPI, or this stands for threads per inch. Okay, threads per inch, TPI. And I'm going to make another box here. Hopefully it'll convert it. And it didn't convert it for me. All right, so threads per inch, that's the other box. So there is a relationship between these two that are going to be our two main equations that we have to learn about for screws. One of them is going to be P is equal to 1 over TPI, or if we solve for TPI, is going to be 1 over P. So these are the equations that we're going to have to kind of keep in mind. Okay, so pitch is equal to 1 over threads per inch, or threads per inch is equal to 1 over P. All right, well, how do we use it and how are we going to calculate with it, et cetera, et cetera? A screw isn't just for holding things together. We can use the screw, and you can look in the book starting on page 90. It can be used to carry water up a hill. It could be used for clamping, for squeezing, for breaking things, all kinds of stuff. If you've ever seen one of these, this is called a vise, bench vise, and you put something in here and you crank on that wheel, it is going to be really, really strong. We've also seen how if you have a screw jack, if you've ever had to lift a car where you had this little thing you put underneath your car and you turn a bunch of times and the whole car uh, rises up. That is using something called a screw jack. So extremely powerful. Let's go ahead and start calculating a few of these things. All right. The other equation that we're going to need to know is IMA, or ideal mechanical advantage, just like all the other simple machines, um, for this group. And this one's going to be 2 pi RE over P. What is this? And once again, this is also coming from the book. The circumferential distance traveled by the effort in one revolution divided by the pitch. In other words, let me erase some of this in here. If you may have noticed, let me go back to this guy. This here, this is turning in a circle. That's the effort that you're making, and your effort is going around in a circle. How big is the radius of this effort, right? If we have this arm, this be this long, that is going to be the radius the um, um, of the effort. So that's what we're going to be using to calculate ideal mechanical advantage. 2 pi r e divided by p, in other words, the number of threads per inch. Now, if you have a lot of threads per inch, or you have a big R, it's going to make a big difference in your calculations, and we're going to talk about that in just a second. Okay, so hang tight. So one other thing we're going to need to learn about screws and how do we define them is measurements. So we have something called a major diameter. So whenever you have a screw and you go to Home Depot and you're going to try and find a 1/4 inch, 1/2 inch, 20 millimeter screw or whatever, you're going to need to know obviously how big it is. The major diameter is going to be the most important part. You're also going to have the length of the screw in addition to the diameter, and also either the threads per inch or the pitch. So we have two different ones. We have the imperial and we have metric. Of course, we can't just stick with metric, but hopefully we can sort these out. Let's start with the metric. If you notice here, the number says M24 times 3. What does that mean? Well, if you notice at the bottom, you have 3 millimeters. That is the distance between the threads. So our pitch is going to be 3 millimeters. Now I say, well, what is going to be my TPI if I wanted to know that? Well, TPI is going to be 1 over P or 1 over 3 millimeters. But we're not going to worry about that right now. And then what about the M24? M24 talks about how long this is. So this thing here is going to be whether it be a 1 inch or whatever. So the M24 times 3, this here is going to tell us the M24 is going to refer to the major diameter and the 3 refers to the pitch. The one number that we don't have is what is the overall length of the screw, and that is typically given as a separate number. So this here could be a 100 millimeter screw, or if it's United States, it could also tell us it's a 3-inch screw or whatever, but it is an M24 times 3 because it is a 24 millimeter major diameter with a pitch of 3 millimeters. In other words, the distance between each thread. On the imperial side, we have 1-8 UNC. We don't have to worry about what UNC means. UNC is just a standard used in the United States. But instead of the 8 giving us the pitch, the 8 is going to give us the threads per inch. So this one here says that it is 8 threads per inch. So TPI is equal to 8. That's supposed to be an 8. And it's got a 1-inch major diameter. 1-inch major diameter. And once again, the total length of the screw is going to be a completely separate number. We could say that this is a 3-inch long screw with a major diameter of 1 and a threads per inch of 8. Now, if we wanted to figure out what is the pitch for this one, once again, it would be 1 over the TPI or 1 over 8. All right, so hopefully that makes some sense. So let's go ahead and do an example. This picture here is of something called a nut splitter. And what you do is you put this around a nut, and I'm going to try and draw a small, well, the nut goes in here. There's a better picture of it on page 93 of your book. But let's say you have a nut that is completely stuck, you need to break it off of the bolt. And it could be that you've got that's something that's been sitting outside for a long time, it's rusted and whatever. So you use something called a nut splitter. You put this over it, and you are going to turn this screw. That's going to push this little part of the cutting tool into the nut and split it. It does take a lot of force if you think about it. It's metal, and it's going to take quite a bit. But on this particular example, they're telling us that we have an AMA, an actual mechanical advantage of 750. Let me read the whole example. A nut splitter is used to remove a nut from a bolt. A wrench is used to turn a 1/2-20 screw that pushes the cutting tool into the nut. The effort force is applied at a radial distance of 10 inches. 2,000 pounds of force is required to split the nut. The AMA of the screw is 750. And I'm basically going with the problem that is on page 93, but I'm going to take it step by step with you guys. So the first part of the question is going to be, what is the pitch of this screw thread? What is the pitch? Well, I already have my equations here. I left them here on purpose. The pitch in this case is going to be 1 over the number of threads, right? So 1 over the number of threads. Well, this here tells us that we have a 20 1/2-20. And when I mentioned earlier, if you have a 1-8, 8 is the number of threads per inch. In this particular case, this 20, that right there is our TPI, or our threads per inch. So our pitch is going to be 1 over 20. Now, we can go ahead and make it into decimal. So we have 0.05 inches, because this is the number of threads per inch, right? So the pitch is 0.05 inches. That is the distance between the top of one thread to the other. The next thing we're going to need to answer is, what is our ideal mechanical advantage for this particular setup? All right, so IMA, we have the definition here, 2 pi RE over P. So what is it that they give us? Well, 2 pi. Well, let's go ahead and 2 times 3.14. And this here tells us that the force is applied at a radial distance of 10 inches. There's a good picture on page 93. I didn't put that on there, but that means that we have a wrench that's going to stick out 10 inches. And then we're going to turn at the end of this wrench, kind of like the way we had on the vise. Whereas the handle here is going to be the same thing as using a wrench. So you can imagine that our handle here is 10 inches. That's going to be our radial distance. So we go ahead and put 10 inches. All right, and we go ahead and divide that by P. Well, what's P? We already had 0.05 that we figured it out. So that goes in here, and that's going to be 0.05. And you go ahead and calculate that out, giving you an IMA of 1,256. Think about it. That is force that has been multiplied by over 1,000 times by using a screw. Because if you try to break that nut with your hands, it's impossible unless you are, some sort of a cyborg. You're not going to be able to squeeze and break that metal piece. But if you use the power of a screw, you can multiply your effort. In this case, IMA 1,256, which is crazy. They did tell us that the AMA, the actual mechanical advantage because of friction and losses and all that other stuff, is only 750. Well, only, that's still pretty big. So if I ask you for the efficiency, remember this little N kind of a symbol is AMA divided by IMA. Something else that you should probably remember. Actual mechanical advantage over ideal mechanical advantage. And if we go ahead and divide that, we have 750 by 1,256, giving us 0.6 or 60%. So that is our efficiency. We have an efficiency of 60% with this particular screw. So we have a huge mechanical advantage with the screw. And something that is really going to illustrate that is when we go to calculate what is called the ideal effort force. The ideal effort force is going to be what is it that we're going to have to put in on our own with our own hand. This particular problem says that we need 2,000 pounds of force to split the nut. Well, we're not going to be able to do the 2,000 pounds by hand, but we can increase our mechanical advantage by 1,256 times. That's the ideal, right? So if I take 2,000 pounds, 2,000 pounds, and I'm not really going to have to lift or push or squeeze 2,000 pounds worth of effort. I'm going to reduce that by 1,256. So really the amount of effort that I'm going to have to put in, and this is the ideal one, as I just mentioned, is only 1.6 pounds. So when you go to turn it, you only have to put in 1.59 pounds worth of effort. That's ideal, right? So this is going to be effort, and that's going to be ideal on it. So what is the actual? Well, in that particular case, instead of dividing by 1,256, which is the IMA, you divide it by the AMA, which they gave us was 750. So you divide your 2,000 by 750, giving you 2.67 pounds. And so that is how much actual effort you are going to have to put in order to turn that screw. So this hopefully illustrates for you how powerful a screw is, and which is why it is used all over the place in our modern as part of our modern tool set.